Welcome to AI Paper Swap. Today we're looking at audio interaction, a unified streaming model for online audio instruction following and voice chatting. It's brand new work from researchers at NTU, NUS, and CUHK. And, for the next 60 seconds, I'm just giving you the high-density download of why this architecture actually matters for anyone building ML models.
Let's hear it.
Right. So currently, large audio language models like Qwen Audio are just entirely offline. They require the full audio clip to finish before they even begin processing.
Yeah, they're completely passive.
Exactly. And on the flip side, you have streaming models like Moshi, which are built for real-time voice chat, but they are highly specialized. I mean, they basically ignore environmental sounds completely.
Right, they just filter the room out.
Yeah. So this paper bridges that exact gap. It introduces a unified, always-on LALM that runs this continuous perceived decide-respond loop over 400 millisecond audio chunks.
Which is incredibly fast.
It really is. Mechanically, it uses a single attention head to emit either a silent or a response token. And by physically decoupling the encoder and the decoder using this asynchronous FIFO queue, they drop first chunk latency to under 400 milliseconds.
Wow.
Yeah, so the result is a single model that follows instructions, translates in real time, and, proactively intervenes if it hears a critical event like a fire alarm.
I mean, that is the core breakthrough right there. We're really looking at a fundamental shift in how acoustic inputs are handled. We're moving from discrete turn-based processing to continuous ambient intelligence.
Right.
But, to appreciate how they achieve this mathematically, we really have to examine the architectural gap that made this research necessary in the first place.
Okay, let's unpack this. Because historically, we've been constrained by the standard offline formulation, right? Mathematically, it's just represented as y equals f of x and a, where a is the fully observed audio clip.
Read like models like LAVA or the base Qwen 2.5 Omni, they just process this clip passively.
Exactly. They are incredibly powerful, but think of them like brilliant scholars who just completely refuse to use a phone.
That's a great way to put it.
Right. You have to record your entire question on a cassette tape, mail it to them, wait for them to listen to the whole tape in silence, think about it, and then, mail you a cassette tape back.
If we connect this to the bigger picture, it is a highly accurate process, but it is fundamentally asynchronous.
Yeah.
You just cannot have a dynamic, fluid interaction with a system that demands the entire context up front like that. So to solve for that latency, the field swung way over to the other extreme.
Which was what?
Dedicated streaming models for very, very narrow tasks.
Oh, right. Like streaming ASR models that just do real-time transcription, or architectures like Moshi tailored specifically for voice chat.
Exactly.
But the problem there is they are like conversationalists who are just completely oblivious to the physical room they're standing in. You could be chatting with them and like a glass could shatter or a fire alarm could go off right behind you, and they would just cheerfully keep talking about the weather.
Yeah, they're acoustically blind to anything that isn't speech.
Right.
And moving from those two extremes, the slow, omniscient scholar and the fast, oblivious conversationalist, to a true large audio interaction model surfaces two massive engineering challenges.
Okay, what's the first one?
The first is comprehension-grounded response triggering. When you're processing continuous, open-ended audio, the model has to decide when to speak based on the unfolding semantic context, not just simple acoustic pauses.
Because, human speech is really messy. Like a half-second pause could mean I'm done talking, or could just mean I'm trying to remember a word.
Precisely. If the model relies solely on voice activity detection, just looking for dead air, it will constantly interrupt you mid-thought. It needs to actually comprehend the semantics of the sentence to know if the thought is complete.
That makes a lot of sense.
And the second challenge is real-time context continuity. To achieve low latency, you must chunk the incoming audio.
Right.
But chunking inherently breaks long-range temporal context. You're slicing a continuous waveform into arbitrary segments. And, you can't just instantly inflate the language model's inference window to stitch it all back together without introducing massive computational overhead.
Which completely defeats the purpose of a low-latency streaming model.
Exactly.
Okay, so they need to slice the audio but maintain the memory. That brings us to the actual engineering solutions the researchers implemented here. They built this model to consume audio in 400 millisecond chunks.
Right.
And at every single step, it predicts a streaming control token, literally deciding between a silent token and a response token. But I actually have to push back on this chunking concept.
Yeah.
Well, imagine trying to understand a complex movie plot while only looking through a peephole every half second. Doesn't chunking completely destroy the model's big picture memory of the sound? Like, how does it keep track of a sentence that started 3 seconds ago?
That is exactly the risk. And it's why their implementation of asynchronous FIFO inference is the absolute linchpin of this entire architecture.
Okay, walk us through the mechanics of that decoupling. How does that actually work in practice?
So in a standard autoregressive setup, the encoder, which listens to the audio, and the decoder, which generates the text, are locked together in a synchronous loop.
They have to wait for each other.
Right. But here they decouple them using a first in, first out, or FIFO queue. Think of the encoder as a pure, relentless producer. Its only job is to continuously crunch those 400 millisecond audio chunks into feature tensors and just push them into the FIFO queue.
So it doesn't care about the text at all?
Not at all. The decoder, on the other hand, acts as the consumer. But it doesn't process every single chunk the moment it arrives. It only drains that queue and updates its key value cache, its working memory, when it hits an interruption point.
Or when the encoder explicitly pushes a feature that triggers a response.
Exactly. And the data on this architectural choice is just striking. The paper shows that without this FIFO decoupling, if you force the encoder and decoder to stay locked together, the average first chunk latency sits at 831 milliseconds.
Wow, that's pretty sluggish.
Yeah, and it has a 5.2% stall rate. But when you decouple them with the FIFO queue, that latency drops dramatically to 392 milliseconds.
That's a huge drop.
And the stall rate drops to exactly 0.0%.
Now, wait a minute, I have to interrupt here. In machine learning, nothing is ever exactly zero. How are they measuring a 0.0% stall rate? Is that just a rounding error?
It's an operational zero based on their threshold for processing time versus chunk duration. A stall in this context just means the system took longer to process the chunk than the actual length of the chunk itself, so it falls behind real time.
Oh, I see.
Because the FIFO scheduler prevents the decoder from constantly waking up to process stale silence, the compute overhead stays so low that it literally never falls behind the 400 millisecond real-time ingest rate during their testing bounds.
That's a testament to the efficiency of the queue. If the encoder is just hearing background hum, the decoder just stays asleep.
Exactly. You aren't wasting GPU cycles thinking about nothing.
Right. And they didn't just guess that 400 milliseconds was the right size. They actually ran ablation studies on the chunk size itself.
Yeah, they did.
If you drop the chunk down to 0.2 seconds, so 200 milliseconds, you completely destroy the semantic context. The model score on the MMAU benchmark, which stands for Massive Mixed Audio Understanding, basically testing its ability to comprehend complex audio, it just plummets to 49.7.
Right, because 200 milliseconds isn't enough acoustic runway to capture a full foam or a meaningful micro event. You're slicing the audio so thin that the pieces just become unrecognizable noise.
Exactly. But if you go the other direction and increase the chunk to 0.8 seconds, you inflate the latency to 786 milliseconds, which feels really sluggish to a human user. So 400 milliseconds is basically the mathematical sweet spot.
Yeah. It captures enough acoustic data to hold meaning, but it's fast enough that human perception registers the model's response as instantaneous.
And this brings us to the internal mechanics. Here's where it gets really interesting. When we look at what the neural network is actually doing under the hood, we see some truly remarkable emergent behaviors.
Yes, the ablation studies reveal two major aha moments that just blew me away. Observation 1 goes back to that continuity problem we talked about.
Right. When the audio first goes through the encoder and the projector, it outputs these highly fragmented representations. The paper measured something called the boundary to internal continuity ratio.
And at this early stage, that ratio is just 0.25.
Yeah, to put that in perspective, the audio data essentially looks like shattered glass to the model.
At that point, the network just sees isolated, disconnected 400 millisecond snapshots.
But here's a mind-blowing part. By the time that shattered data hits GPT layer 0, the very first layer of the language model, the network instantly reconstructs this continuity. The ratio shoots from 0.25 up to 0.80.
Wow.
And it does this through cross-chunk KV cache access. How is the AI actually doing that? We didn't explicitly program it to glue those pieces together.
It's wild. It is experiencing audio as shards of glass, and the very first thing its brain does at layer 0 is instinctively reach back in time. The attention mechanism expands its window backward, grabbing the representations from previous chunks stored in the key value cache.
And just glues them back together into a continuous timeline.
Exactly. It figured out object permanence for sound.
Object permanence for sound. That is exactly it. And then there's observation 2, which is arguably even more fascinating. It's about the trigger mechanism.
Right, the attention heads.
Yeah, the network has 576 attention heads in total. But through the training process, the model learned to route the entire decision of whether to output a silent token or a response token through one single attention head.
Layer 35, head 14.
Exactly. If you ablate, meaning if you artificially turn off just this one specific head out of the 576, the model loses its ability to stream properly entirely. Its speech-to-text translation match scores drop by a massive 0.88.
Which basically means the entire streaming capability collapses without that single node.
Right. It is like finding a single, hyper-focused bouncer at a chaotic nightclub who holds the absolute, unquestioned authority on when the model is allowed to open its mouth. Everything has to go through him.
What's fascinating here is, to expand on your bouncer analogy, this isn't a bouncer who's just checking IDs at the door.
No.
No, this bouncer is standing in the middle of the club, analyzing the rhythm of the music, reading the semantic tension of the crowd, and listening for acoustic drops, all simultaneously, to decide the exact millisecond to open the door.
That's incredible.
What is so elegant about this is the abstraction. The network naturally routed a highly complex, multitask streaming decision through a narrow, task-independent pathway. It didn't build a separate trigger mechanism for speech recognition, and another one for translation, and another one for casual chatting.
It abstracted the entire concept of interruption into a single universal circuit at layer 35, head 14.
Precisely.
Which begs the question, how do you train that bouncer? Like, how do you teach layer 35, head 14 to know the difference between an awkward human pause where it should stay quiet and the actual end of a sentence where it needs to jump in?
You definitely can't just throw standard offline data sets at it.
Right. So the researchers had to build the SOUNDFLOW Framework and this massive data set called STREAMAUDIO-2M. We're talking about 302,000 hours of audio, 2.6 million items spread across 28 interactive subtasks.
And the linchpin of this entire training process is the Time-Frequency Joint Preprocessing Module, or TFJP.
Unpack that for us. What does it do?
Well, the TFJP module solves a critical problem in synthetic data generation. When you're synthetically stitching together different audio clips to train a streaming model, you run a huge risk.
What's the risk?
If you just glue an audio file of a person speaking directly onto an audio file of silence, the background room noise abruptly cuts out at the exact splice point.
Oh, right.
And neural networks are notoriously lazy. They will just take the path of least resistance. Instead of learning to understand the semantics of the sentence to know when to trigger a response, the model will just learn to listen for that sudden acoustic dead zone as its cue.
So it just listens for the audio glitch instead of the actual conversation?
Exactly. It learns the artifact, not the task. So the TFJP module physically stabilizes the synthetic audio. It clips excessive silence, but more importantly, it estimates the background noise profiles of the clips and physically smooths the boundaries of the audio splices.
So it makes the transition seamless.
Right, so the model is forced to actually comprehend the language to know when to trigger, because it can no longer cheat using audio artifacts.
But even with clean data, you still have to mathematically teach the AI when to speak. How do they actually penalize the model during training for speaking at the wrong time?
They fundamentally changed the loss function. They introduced a dual loss objective. Mathematically, the total loss equals the standard LLM loss plus a streaming loss, and the balance between them is controlled by a weight parameter called lambda.
Unpack streaming loss for us. What does that actually look like to the model?
So the standard LLM loss trains the model to generate the correct words. The streaming loss specifically penalizes the model for the timing of its control tokens using cross-entropy. If the model emits a response token while the human in the audio is still speaking, the streaming loss spikes.
And if it emits a silent token long after the human is finished and asked a question?
The loss spikes again. They tested different weights for lambda and found that setting lambda exactly to 1.0 proved to be the optimal balance. It forces the model to weigh semantic comprehension and conversational trigger accuracy equally.
But even with that perfectly balanced loss function, you still face what the paper calls the dominant failure mode in production for these models, which is over-triggering. I mean, nobody wants an AI assistant that interrupts every time you take a breath, or clear your throat, or shift in your squeaky chair.
Precisely. To counteract over-triggering, they implemented two brilliant training strategies. First, they used history review prompts. They explicitly forced the model to recall information from 3 or more conversational turns ago.
So this forces the KV cache to maintain long-range context rather than flushing it every time there's a pause.
Exactly. And second, and crucially, they use silent audio verification.
This is where they train it on when not to speak. Right.
Yes. They explicitly fed the model Non-speech clips, just ambient room noise, typing, coughing, and audited it against strict safety criteria. If the model fired off a response to a harmless daily sound, it was heavily penalized.
Without the specific verification step, the model would basically constantly try to converse with your air conditioner. Okay, so the architecture is solid, the bouncer at layer 35 is trained, and the loss function is dialed in. Let's look at the hard metrics.
Yeah.
When you actually drop this into a chaotic environment with unpredictable noises, does it hold up?
The short answer is yes. Despite being an always-on streaming model, it completely maintains its offline capabilities.
Yeah, we mentioned the MMAU benchmark earlier, Massive Mixed Audio Understanding. It hits a 58.15 on MMAU, which actually beats the baseline model it was initialized from.
Which is really impressive.
And for translation, it improves Kobo's 2.2 English to Chinese BLEU scores by plus 15.72. For those who might not know, the BLEU score is a standard metric for evaluating machine-translated text against a high-quality human translation. A jump of 15 points is massive.
Oh, absolutely.
Yeah.
But the real magic is in the proactive Soundbench results.
Yeah, this is where we see the shift from reactive to proactive. The paper details some incredible real-world case studies. In one scenario, the model is just listening to the ambient room. It hears someone coughing heavily, and without being prompted, it proactively intervenes and says, "Drink some warm water."
Wow.
In another, it hears a fire alarm in the background and immediately states, "Stop work immediately and evacuate."
It is stepping out of the role of a passive tool that sits on your desk waiting for a wake word and into the role of an active agent monitoring an environment for safety and utility.
So what does this all mean? For anyone listening who builds or researches ML models, this is basically the holy grail. We are shifting from reactive prompting to proactive context-aware agents.
Well, let's be real, it is not flawless.
Right. When you look at the error analysis, you start seeing the cracks. On the LibreSpeech benchmark, 60.2% of its errors are categorized as local token deviation. What does that actually mean in plain English?
Local token deviation basically means the model gets the big picture right, but fumbles the micro details locally. It understands the semantic meaning of the sentence, but it might mispronounce a specific word, hallucinate a slight variation of a noun, or drop a plural.
Okay, so it's a localized error that doesn't necessarily derail the whole conversation, but it affects the precision.
Right. And this raises an important question because the errors get more pronounced when you move from benchmarks to real-world environments like travel, work, or home scenarios.
Oh yeah, the false positives are almost entirely triggered by daily sounds. It hears tearing paper or a loud appliance spinning up, and it thinks it needs to intervene.
And worse, the false negatives cluster in safety-critical domains. It actually missed certain traffic alarms in their testing.
Which really highlights the massive gap between synthetically mixed training data, even with that TFJP boundary smoothing we talked about, and the sheer unpredictable acoustic chaos of a busy street corner or an active kitchen.
The model is undeniably brilliant, but the fact that it still confuses the sound of tearing paper with a critical environmental event shows that our latent audio spaces are still quite fragile. It's a huge tension in the field right now.
It's the classic difference between learning in a sterile lab and operating in the wild. Which brings us to a final provocative thought for this deep dive. We spent this whole time looking at the mechanical genius of this model, the FIFO queues, the KV cache, the streaming loss. But let's zoom out and look at the horizon.
Okay.
If a unified streaming model can continuously monitor a room, seamlessly running its 400 millisecond loop, if it is proactively intervening based on nonverbal cues like a sigh, a cough, or the clinking of a glass, where exactly is the boundary between a helpful assistant and a constant observer?
That is a profound philosophical shift. We are actively engineering systems that don't just process our explicit commands, but quietly monitor our physical state and our ambient environment.
Exactly. If layer 35, head 14, our hyper-focus bouncer, is always listening, always deciding whether to trigger a response, what happens when it starts interpreting emotional subtext or physiological distress that we didn't even realize we were broadcasting?
Suddenly, that brilliant scholar we used to mail cassette tapes to isn't just in the room with us. They are monitoring our heart rate through the acoustics of our breathing.
It is an incredible technological leap, but it completely redefines our relationship with our immediate physical environment. Thank you for tuning in to AI Paper Slop. Keep building and stay curious.